Okay, we're gonna do two things. We're gonna practice inverses of logs, and keep in mind that logs are the inverse of an exponential. So, for instance, the inverse of 2 to the power of x would be log base 2. Normally, logs are base 10 unless you say a number here of x. This will produce the exact opposite xy coordinates of that. Whatever the exponent base is, it will be log, the inverse will be log base 8. So it's very important to be able to spot the ace from the exponent, especially when there's all sorts of um, translations, transformations, like this. It's very easy to believe 3 is it, but it's whatever's over, the x is over, that is the base. And the log base will not change. Now I'm going to teach you the long proper way of doing a log, and we're going to do any transformation can have essentially 4 or technically 6 transformations. There's 2 y transformations that you'll see at the very beginning and the very end. There's 2 possible x transformations that you'll see right beside the x. And these will be stretches or compressions, and these will be translations up, down. These will be stretches, in this case a compression. And these will be translations right or left, in this case to the right. There's 2 more technically, negative numbers. And it's important to understand what a negative number does. We'll get to that in a second. So technically I would count those as 2 extra. A negative beside an x is actually a reflection in the y-axis because it changes all the x values to negative. And a negative by the y is actually a reflection in the x-axis. These are terms you'll need to learn, but let's just look first. I want to show you an exponential. It's 3 in the front. We're going to use a 5 base. It's to the power, and I'm going to even have transformations to this x. Be aware, teachers love to show the x transformation incorrectly as this. In reality, you cannot have a number or a negative in front of the x, so you should be factoring out the number to get the true translation. And this. There are 4 transformations here. These are the y's. These are the x's. Now, before I teach you how to do an inverse, so this would be f of x is equal to this, I want you to list these transformations as you've learned them. Focus on the x transformations if you wish first. Remember that x lies. So looking at that 2 in front, that's not a stretch. That is actually a 1 over 2. So it's a compression. So it lies. It's the opposite. What you would do is you would multiply all your x values by half. So you would take the parent x values and you multiply it by half. And that negative 2 by the x is not moving to the left by 2. It's 2 horizontally to the right. So after you multiply all your x values by half or divide by 2, you would then add 2 to them. I'm going to skip the written version. These are the x transformations that are going on. Now the y transformations. Y does exactly as you think. There's a 3, so it's a stretch by a factor of 3. And then there's a vertical translation up by 6. Now, what about an exponent? An exponent, normally, the parent function, all the y values have a restriction, bigger than 0. As soon as we raise it up by 6, it's going to be bigger than whatever that number is. So we would put an asymptote at x is equal, y is equal to 6 rather, and my graph would now go from there. And I would use 3 or 4 points to do it. Before I teach you the algebraic way, I want to teach you the cheat method. The cheat method is very interesting. So for this one, the domain is XER, and the range is y must be bigger than 6. What happens in inverse? Every y thing becomes an x thing. Every x thing becomes a y thing. All these x translations become the y translations, and all these y translations become the x translations. Now look how quickly I can cheat. So I'm just going to move these up and shrink them a little bit. Like that. That means on my inverse graph, instead of coming up with the numbers, I know that my x, sorry about that, my x will do whatever the y does up above. So it's a stretch by a factor of 3 for my x, which means I would have to put a third in front of it. And it's vertically up by 6. So up for x is right. So it's a moving horizontally right, translated horizontally right by 6. But in the x, what we would write for x, because x lies, is x minus 6. So I would put a third in front of the bracket and x minus 6 to get it horizontally right by 6. Now let's look at our y transformations. It's exactly whatever the x says up above. Whatever the x says up above. So our y translations for this will be, I'll just put y there. It's going to be compression by a half. So it's going to do exactly as it says. And horizontally to the right is 2 up. So vertically translated 2 up. Now look, I can just, now I know I'm going to be, what base is up here? 5. Oh, and here's the domain and range. So the domain and range of my inverse is going to be x is bigger than 6 and y ER. So y goes on forever. Suddenly, I have enough information just from correctly reading the translations of this one to do the formula for this one. Notice it's a base 5. So we're starting with f of x is equal to log base 5. I'll put the 5 there in a second. But notice that I have my x translations. I need a third, so I'm going to open bracket, a third. And my x translation, I need to move it 6 to the right. So there we go. I'm going to do that. I'm now going to put the 5 here. Now, what are my y translations? Well, I have a compression of a half. And it's vertically 2 up. So it's plus 2. Boom. I've now correctly done my point. And if I had 4 points from this one up here, I would just swap their x, y values. And I now have 4 points down here. Boom. Remember, this is a plus 2, not a multiply of 2. There. I should, if I do the algebraic method, come up with the same thing. This is a very interesting cheat. Notice the connections here. There's a 2 by the x, which is actually dividing x by 2, becomes a half over here. There's a minus 2 here, which becomes a plus 2 over here. There's a plus 6 on the y here, which becomes a minus 6 on the x. And there's a 3 on the y here, which becomes a third here. So you can even see the connections. I can immediately graph this and say, okay, from x6 is the now the asymptote. Normally a log graph looks like that. This one's been elevated by 2, so it's going to look something like that. I could just use the 6 points and run through them, or 4 points if I want. I'm not doing 4 points here. I just wanted to show you how I do it. How would you do 4 points? Well, you would not find 4 points on this graph. Sometimes that'll take forever when you're doing an exponent. Instead, you look at the base 5 graph and you say, okay, well, 5 to the exponent of x would produce, when x is 0, y would be 1. When x is 1, y would be base. That's all the two numbers you always have, 0, 1, 1, 5. If your teacher only wanted 2 points, you could use that. But I could also keep going. When x is 2, 5 squared is 25. And if you want, you can do minus 1. When x is minus 1, 5 to the negative 1 is the same as 1 over 5. I now have 4 points. Let me reverse those for my other graph. My x and my y values for my other graph will be a fifth, comma, minus 1. Because we're swapping x and y's, that's what inverses are. Whoop. I now have 4 points on my inverse graph. So now I would go down to this one, and I would say, okay, well, there's a 1, 0. 1, 0 is right about there. Oh, wait, we haven't translated them. Yeah, we haven't translated them. My bad. So I have to divide all my x values by 2 and then add 2. When I divide by 2, it's the same as multiplying by a half, if ever you come across that. But this becomes negative a half. And then when I add 2, it becomes 1.5. So this x value is 1.5. This 0 divided by 2 is still 0, and when I add 2, it becomes 2. Notice I'm going up by 0.5. This 1 becomes minus 1. Sorry, when I divide it by a half, it becomes a half, and when I add 2, it becomes 2.5. Oh, there's a pattern there. This 2, when I divide it by 2, becomes 1, and then when I add 2, it becomes 3. Notice they all went up by 0.5. This a quarter, now when I multiply it by 3, becomes 3/5. And when I add 6, I'm just going to say 6 3/5 for now. You could do 33/5 if you wanted to. This 0, when I multiply it by 3, is 0, and add 6, I get 6. So I got 2, 6. And this 1, 5, this 5, when I multiply it by 3, I get 15. When I add 6, is 21. And this last one, yeah. When I add this last one, when I multiply 25 by 3, I get 75. And when I add 6, it's 81. So these are the 3 points on this graph. To find my points on my new graph, this is what I reverse. My mistake. You go 6 3/5, comma 1.5, 2, 6, 2.5. Oh, yeah, I got it. 2.5, 21, and 3, 81. Might have made a math mistake in there somewhere, but I don't think so. So 6 3/5 is just to the right of my new asymptotes, 1.5. It's here. It's because everything got elevated by 2. 2, 6. 2, 6. And let's see, is here. Well, 2, 6 is here. And then let's see, 2.5, 21 is way up here, and 3, 81 is way up here. So I get this. Really stretched, right? It's really stretched. Sorry, it's really compressed, rather, by a third. That's making it do that. And then it's compressed again here. So this makes it fatter. But those are the 4 points I would run through. I just find the 4 translated points on this one and swap their x, y's, because that's what inverses are. Let's look at how to do these things algebraically. There we go. I'm not going to start with this. I'm going to start with the parent one. So suppose you have f of x is equal to 5 to the exponent of x. Your first step, swap f of x for y. You get y is equal to that. Your second step is to realize there's no way to bring an exponent down. Oh yeah, your second step is swapping your x for your y and your y for your x. That's what an inverse is. Desmos, if you put that in, will actually draw the inverse from that. But your teacher does not want that, so we're going to bring it over here. The only way to bring an exponent down is to use logs. So you're going to take a log of both sides. From this, the rule of logs say I can bring the exponent down. If you don't understand why, go by other things. Go look at other things. But I'm allowed to rewrite this as this. Y in front as a multiplier. Log 5 is just a number, so I can divide both sides by log 5. So I get y is equal to that. And you might say, well, that doesn't look like something I know. Y is equal. This is indeed the proper graph. However, now you have to do another rule of logs that says when I divide one log that's base whatever, divide by the other log that's base whatever, in this case 10, I'm allowed to use this as the base and this as the log. So I'm allowed to rewrite that as log of x base 5. If you don't believe me, take a log of any number, let's say log of 8, which we know is the answer to this we don't know, and the log of 2, the answer of which we don't know, because it's base 10. However, I'm saying that's the same as log 8 base 2. The answer to this I do know is 3. So if I take log base 10, 8, divide by log base 10 of 2, I should get the answer 3. And I do. So that's a rule of logs. When you have two logs that have the same base, you're allowed to put the 5 as the base, x as the main, and rewrite it like that. So that means, boom, we're done. That's the inverse. Y is equal. Oh, I don't want to delete that one. I want to delete the other one. That means I can rewrite this as y is equal to log base 5 of x. And now you've got to reintroduce your f of x, but for an inverse, we usually put a -1, I think is how they're notating it now. So you put the 5 there, and you put, I believe, the -1 over the f. And that denotes that we found an inverse of the f of x that we were working with. If that's not the correct notation, confirm with your teacher for the correct notation. So those are the steps for finding that when it's just got nothing to it. What happens when it's an exponential graph that has a number multiplying it in front? Well, this is the same base 5. Well, it's the same steps. Replace this with y. Swap your x and your y values to start and figure out how to get your y isolated. Now, what's interesting is when there's an unknown in an equation, the best technique is to do what's called reverse bedmass. So we know bedmass is brackets, exponent, division, multiplication, addition, subtraction. So first you find any subtraction or subtraction outside of brackets, of course, and not in an exponent. And you do those first. You do the reverse of those. Then you find any division, multiplication outside of a bracket, of course, or outside of exponent. You do that next. Then you do addition, or then you do the last one, or exponents next, and then brackets next. Brackets last. Brackets always last. So let's look. Is there any addition and subtraction? No, there's not. Is there any division or multiplication outside of brackets or outside of an exponent? Yes, there is. So it's the reverse of multiplying by 3. We divide by 3. Now, I want you, instead of dividing by 3, get into the habit of multiplying for these by the reciprocal, because it'll make the translation more visible. So we're going to multiply by 1/3. Anytime you multiply a number by its reciprocal, and by the way, -1/3 is not a reciprocal. A reciprocal is just the upside down of the number. So the reciprocal of 3 is 1/3. And that's because 3 technically is over 1. The reciprocal of 7/9 is 9/7. If we were to multiply these two things, the 9's cancel, the 7's cancel, we're left with 1. So multiplying the reciprocal will always sort of eliminate it or leave a 1 multiplier. Note that if this was -7/9, we'd have to multiply by -9/7, even though this creates a -1 and this creates a -1. There's now a -1 down here and a -1 up here, which creates a +1. So you're always trying to get to a +1. So the reciprocal of -7/9, -9/7, you always put the negative up top. In any case, we just multiply by 1/3 by both sides to get rid of this 3. And now we're back to the same case we were before. Now, you want to put that in brackets. We have to take a log of both sides. And now we can put the y in front. And then you can divide both sides by the log of 5. So you got a log of this divided by the log of that, which means I'm allowed to rewrite it as this, as the base 5. Doesn't matter what's in the bracket. I'm allowed to do it like that. So this is a base 5 log is equal to 1/3 x. Notice that before it was 3 times y, which was a vertical stretch of the y. And this is technically a horizontal stretch of the x. Even though it's written as 1/3, it does the opposite because x lies. And then finally replace that with f of x. And put the little -1 up top. Now let's go back and add some complexities to it. Now we're going to add another y value. We're going to keep these rules in mind on the top right. And we just have to live with that. We're going to add a 7. Now we're going to go through our checklist again. We've already swapped the x's and y's. We're trying to isolate y. We have to follow this rule. Is there any subtraction addition outside of brackets? Yes, there is. So we must subtract 7 from both sides. It cancels on the right, which is why we did it. And then we go back to the same thing we just did. We have to now go to the next any division multiplication. Yeah, we multiply by 1/3. And just keep this first thing where you subtracted 7 in brackets. And when you multiply by the 1/3, create a new brackets because, and by the way, the multiplying by 1/3 got rid of this 3. Because That's what you would do with an x transformation anyway. You'd create brackets around the subtraction, division, addition, and then have another bracket around the multiplication. Then, of course, we have to take a log of both sides here. It's the same steps as before. Then you're allowed to take the 5 and put it, or the y and put it in front as a multiplier. And then, of course, log 5 is just a number, so you divide both sides, or multiply by the reciprocal, since I've said that before. But a log of 5 and a log of whatever this is allows me to put the 5 here as base. Doesn't matter what's in the brackets. That's the rule. You get to follow the rules. And finally replace this with f minus 1 of x. Notice that before it was a y translation 7 up and a stretch of 3, and this is still a stretch of 3 and a translation 7 to the right, which is the equivalent of up. So you can see the transformations right in there. And then you just keep adding complexity, right? You can now even put a negative 3 if you want in there. What happens with a negative 3? So if a graph, log graph looks like this creates a reflection in the y-axis because, sorry, this creates a reflection in the x-axis because it's a y transformation, which means the x-axis is down here, which means instead of going up like that, it's going to come from this and go like that. If you need to see that, you can always pull up Desmos, is fantastic for this, and just put in a log of anything. And outside, this should be a transformation because it's a y transformation. It should be flipping the x-axis. And sure enough, it goes down to the right instead of up and to the right. If I put a negative on the x, we're going to see a translation in the y-axis because all the x values become negative. Note that when we have a translation on the x, sorry, a reflection on the x, we affect the domain. So now the domain is no longer x bigger than 0. It's x smaller than 0. Also note that had this been a minus, before the minus, had this been a plus 7, it would have, or plus 4, it would have moved 4 to the left. And thus our domain would have become x is bigger than minus 4. If I put a negative here, this flips it in the y-axis, and now my domain becomes x is smaller than, y-axis rather, smaller than minus 4. So be aware, negative numbers by x in logs affect the domain, and negative numbers on the y in exponents affect the range. So you have to learn these graphs by doing it. Now we have minus 3. Do I have any subtraction addition? Yeah, minus 7. So I get x minus 7, and we get rid of that 7. Do I have any multiplication or addition? Yeah, I have minus 3. Now you can get rid of it one at a time if you want. You can say, I'm going to divide by or multiply by minus 1. You just put the minus over here first, and then multiply by the reciprocal, 1/3, to cancel. And again, the rule of math is whatever you do to the left side of the equation, you must do to the right. There's that negative 1/3, or you can just multiply by the negative 1/3 to get rid of it all at once. Keep in mind, if this had said 3/5 as a influence, you could multiply by 5/3, and that would get rid of it entirely. You just multiply by the flip, called the reciprocal. In any case, we don't have to do that. We have minus 1/3, and that would get rid of this minus 3 over here. And we're back to the same thing as before. We take a log of both sides. The y can go down in front. And we can divide both sides by log 5, which essentially just makes this 5 base. There you go. Inverses are key for a lot of things, and you should also learn a very basic one for a reciprocal that says x plus 1, let's say, and x minus 3. Because this reciprocals for, inverses for reciprocals are tricky, and so are these. These are a bit tricky. Those are the only tricky ones. They're well worth learning. Okay, because it's really not hard once you learn. Okay, what happens if I add some more? Okay, this time we're going to add some to our x and our y value, or sorry, our x values. And we're going to jump, and we're just going to we're going to be really mean, and we're going to hit 5/3 up here, and we're going to make it negative. And in brackets, I'm going to have x plus 2, and we're still going to have the x plus 7 here. So right here is all the translations you can have. I have 2 reflections, a stretch, a compression, because it's 3/5, move 2 to the left, and 7 up. If I were to write them all down, I could just reverse them and use the trick to rewrite my equation. It's going to be a log base 5 again. So just looking at this, I can see that I have a stretch of 3. So that would translate minus 3, rather. A reflection in the x and a stretch, so minus 3. So that'll result in a minus 1/3 by the x. I have a plus 7, which is x minus 7. So this is what I'm going to see in the reciprocal. Whatever the y transformations, I'll see in the x transformations. Then I'm going to have log base 5. And then for the x, the reverse of that is 3/5. So I'm going to have negative 3/5 in front here. And plus 2, so I'm going to see minus 2 out there. And it's log base 5. So right there, I was able to just look at the x, y's and put them here for the y. X's for the y's and y's for the x's and come up. So it's going to come out as minus 3 log, minus 3/5 log 5 minus 1/3 times x minus 7 and then minus 2 on the other thing once we do it. So we have to do reverse BEDMAS. And just a moment, I have a knock at the door. Okay, so let's proceed. We must do reverse BEDMAS. So we have to do subtraction addition first. That's not on an exponent or in bracket, not exponent. We have to then do division multiplication, not in a bracket, not an exponent. Then we can do exponents, then we can do brackets. This is an addition that's inside a bracket. This is a multiplication division that's over an exponent. So we can't do those first. Oh, and I forgot. I think it was plus 7. Yeah, plus 7. I can't forget the plus 7. There we go. So we must look at addition or subtraction that's not part of a bracket or an exponent. And that's that one. So we subtract 7 from both sides. Oh, I have to switch my y and my x. We can anticipate a log 5 because I see a log. And the whole point is the reason you're switching them is we're trying to isolate. Okay, so we're going to switch our x and our y's and then go from there. As soon as I get it right, there we go. Good, there's our y. Just put it in there. Yeah, I'm just being particular. So when I subtract 7 from both sides, I get x minus 7. And I'm going to put it in brackets. Then I have to look for additions or multiplication that is not part of a bracket, and that would be this minus 3. This is part of an exponent, so I have to do it last. So I have to now multiply by negative 1/3. That's the reciprocal of negative 3. And it just makes the translations more visible when I do it. And I'll show you what happens if I divide by 3. That gets rid of that. Now, we're on to exponents, so we can move up to this one. We can move up above to this one. And I can see within the exponents, is there addition, subtraction? So we go through the list again. Yes, there is, but it's inside a bracket. So I must do the multiplication first. So I multiply by minus 3/5. Oh, wait, there's nothing I can do to that until I get to the exponent part. The only way I can get to the exponent part, my mistake, is to take a log of both sides. So log and open this bracket. Make sure this is in the bracket, and then log over here. Once I do a log on the right side, I am able to bring the exponent down. That's the whole reason we're taking the log. So I can move this over here. And I can bring this entire exponent down, and then it no longer becomes part of an exponent. Now I can go through BEDMAS again. Is there subtraction, addition? Yes, there is, but it's inside a bracket. Is there division multiplication? Yes, there is. So I multiply everything by minus 3 over 5, the reciprocal of 5 over 3. And that gets rid of this. Now we're into the bracket because we've gotten rid of everything that's affecting it outside the bracket. And we can subtract. What can we do? Oh, wait. We cannot, because this is also multiplying it. This is also multiplying it. So we have to divide it out, both sides, by dividing out both sides, and it cancels on the right. And as usual, a log divided by a log with a different number means I can change the log to a base 5. That's how we get it there. Made a few mistakes on this one. And then finally, I have to subtract 2 from both sides. So I get this. And then also I replace the y with f. Minus 1x to say it's an inverse. Notice I got all the things I predicted. There's a minus third by the x with a minus 7 for a stretch of negative 3 and move 7 to the right. There's a minus 3/5 compression, and there's a down 2 vertically. Everything I described in the translations of the original and then swapping them gave me what I wanted to know. Because this is a reflection in the y and it's moved 7 to the right, the domain is now x is smaller than 7. So move 7 to the right, but then this negative number means it's going, I have to change the sides. So normally without that negative, it would be x is bigger than 7. With that negative, it's x is smaller than 7. Punch this into Desmos to make sure. Just punch this whole equation, and you'll see what I said is true. And that's how you do it algebraically. It helps to understand always how to unravel an equation that's missing, which has a mysterious variable, and this is called algebra.